Hello and welcome back to Calculus 1 section 3.2 on derivative as a function. So we saw in a previous lecture that I had f of x is equal to 3x squared minus 6, I guess, plus 6, doesn't matter. And then we had f prime of x is equal to 6x. Then I had another example, let's go with g, doesn't matter, g of x is equal to 1 over x, and then we have g prime of x equal to negative 1 over x squared, right? So these are just some examples that we discovered last time by using the formula that f prime of x is equal to the limit h goes to 0 of f of x plus h minus f of x divided by h. So that was the formula we derived last time, and that's the formula you use, which is just a basic 2.3 difference quotient limit calculation that you should know by now because it's on the exam, right, coming up. So the next topic here in our calculus series is to talk about connection between the function and the derivative, because you do see that you have a derivative, you have equal, you have a function, right, with a whole bunch of other stuff. So how they're connected at all times, and how we can use the derivative to read important stuff about the function itself, right? And we start by observing a graph that has the function, which would be in black, and the derivative, which would be in red, right, graphed on the same coordinate system right here. So say you have a function that goes like that. That's going to be f of x, black, and now we're going to go with red and sketch the derivative, right? So we're going to sketch the derivative. The way you do that, when the function is given, you have no formula, you have no equation, you can't calculate anything and use the graphing utility. So what you can do is you can learn 4 different concepts that relate the function and derivative graphs, and those give us some insight into the connection between these two worlds. So one of them is the maximum value here will give us a 0 on the derivative, and also the minimum value here will give us 0 on the derivative. So rule 1, min and max of f of x, that's black, gives us x-intercepts for the derivative, which is f prime of x. So the first order of business is to immediately locate all of the min and max values you have, local, global, doesn't matter, and at those points the derivative is going to cut through the x-axis. Now, rule 2 says if f of x is increasing, so if f of x is increasing, f prime of x is positive. And I'm going to call that positive in parentheses above x-axis. It's very simple to spot when something is above and something is below x-axis. And rule 3, now we do not have rule 4 on this picture, so I'm going to wait with rule 4. if f of x is decreasing, f prime of x is negative. Below x-axis. You know what, since I'm listing all the rules, how about I list the fourth one even though it's not on this picture, and then we'll just do the next example. Rule 4. If f of x is constant, so if f of x is constant, f prime of x is equal to 0, which means along x-axis. So those are the rules. So now let's use these rules. So the fourth rule, right? Okay, let's go and look at this now. So what do I have? Before the first point over here, right, I see that the original function f of x, the black one, right, is increasing, meaning that the derivative will be above x-axis. Then, on this region here, right, when I look at the x values, on this region here, we see that the black line is decreasing, meaning that the derivative is going to be negative, below x-axis. And then later on, it's increasing again, which means it's going to be positive. And that will be the sketch of f prime of x. So anytime the black line decreases, red line is below x-axis. Anytime the black line increases, the red line is above x-axis. So those are the rules. You start with min and max. Min and max always have to cut through the x-axis, so that's where the zeros are. You start from those, and then you go through these rules. I forgot another one. Sorry. Let's go. Rule 5. Vertical asymptote for f of x and f prime of x is at the same location. That's a very useful rule. We already had the derivative of 1 over x. We know that 1 over x is the function that goes like that. So that's our 1 over x function. So I'll put that f of x equals 1 over x. So that's in black. And now in red, we want to draw the derivative. Well, first off, I'm going to note that there is a vertical asymptote for 1 over x. Vertical asymptote at x equals 0. And you see that the black function, right, the original function, follows it as it goes up and goes down. So it follows our vertical asymptote. Now, if you consider the rules, one of the rules said if the function is decreasing, derivative is below x-axis. So this one is going to get pretty much the same thing going down. And on the other side, it's going to be also like that, because 1 over x is always decreasing, right? as you are moving from left to right, you are constantly going down, right? You can imagine over here walking down the line. You're walking down the line because it's decreasing to the right. Also, you can imagine yourself, walking on this black line, going also to the right, and because of the shape, down. So we know what the f of x is because 1 over x, we graphed the black line. But now we are using the rules. I am going to use the rule 4, rule 5, which says that the vertical asymptote and the vertical asymptote for f of x and the derivative are at the same location. They're always in the same location. And now that location is x equals 0 for this case. And then we go and we use the rule where it says that if the black line is decreasing, the red line will be below x-axis, and that's how we ended up with the 2 red lines below. Now, that's okay because we know that f prime of x is negative 1 over x squared. On the side over here, 1 over x squared graphs both of these above. So 1 over x squared graphs this above, and then the negative in front of the 1 is the one that flips it on the x-axis. That's what you learned in your pre-calculus course when you learned to reflect and shift functions around. So you see that the difference between the two is just to shift it downwards. In mathematics, everything has to click, right, from all angles. No exceptions. So we see that the vertical asymptote is on the same spot. We follow the rule that the decreasing function, which is decreasing black line, will give us the negative reds, meaning they're both below x-axis. We also know the general shape of 1 over x squared, which is given in purple on the side, and we see that the one on the derivative is flipped, but that's okay because we have negative 1 over x squared. If you go back to the previous section, right, the last problem we did was to find the derivative of 1 over x, right, function, which we found to be negative 1 over x squared. And that's the example we just used over here to show the vertical asymptote rule. A little bit more on this, giving another type of the graph. Let's go. So say we go like that. Then we go 4 squares, 2 in the diagonal, or 3 squares, and we shoot straight down within 2 squares. So this is going to be at 2, this is going to be at 6, it's going to be at 8, it's going to be at 11, and it's going to be at 13, and obviously 0 to begin with. What you need to get used to now is not looking for points. You now have to look for the intervals and what's happening over the interval from x1 to x2. So what is happening with the function from 0 to 2? It's increasing. So the derivative is going to be positive, right? Now, if the derivative is going to be positive, we can also calculate this derivative because I drew 3 squares up and 2 squares over, right? So we know the slope. The slope is 3/2. If the slope is 3/2, that means that our derivative over here is at 3/2, which is 1.5. What is happening with the black function, right, with the f of x, with the black line? What is happening with the function between 2 and 6? Constant. Now, what does that mean for the derivative which measures the change? 0. Do you catch that in the way it's said, the English language? The change of a constant is zero. Yeah, constant things don't change. If the derivative measures change, and we are looking at the constant doesn't change, therefore the derivative over here has to be zero, which means along x-axis, because this piece of the line is constant. Constants do not change, therefore derivative is zero. What is happening from 6 to 8? It's increasing at what rate? 1. Because we are going at the 45-degree line. You go 2 squares up and 2 squares over. 2 divided by 2 is 1. So we go on the elevation 1, and we have a constant change of 1, right? So it's the acceleration. Now what happens from 8 to 11? Also 0, because it's constant. Finally, what's happening from 11 to 13? It's decreasing. Excellent. The derivative is going to be below x-axis. The derivative is going to be negative because we have a decrease. All right, so I'll put a decrease, constant, increase, constant, increase, right? So any constant gave us 0. Any increase gives us positive graph. And now where do I draw the line for this decrease? You said below. At what value? Negative 5 over 2. Right here. Because you go 5 squares down, so that's negative 5, 2 units over, so negative 5 divided by 2, that's negative 5 halves, so that's 2.5. So negative 2.5, right? That's where it is. So you see now that your derivative is some kind of step function, right? It's a piecewise function. It goes all over the place. Another one that might pop up in life is the y equals absolute x. What is going on with the derivative of this thing? So let's draw the function. We know it's a V shape at 45 degree. That's how much you learned, hopefully, in pre-calc. So talk to me. We have a decrease over here. We have the increase over there. Where's my derivative? Where's the derivative? Come on. Talk to me, someone. Yes. For this one is below. It's decrease, so it's below. Now what is its slope for this line? Negative 1. So it's going to be a flat line, negative 1 going towards the x-axis. I mean y-axis, sorry. How about the other side?
Positive.
Positive 1, great. Positive 1 because what do we have? We have a positive slope, the increase. There is a positive slope. What is the derivative? Derivative is just all of the slopes, the m values, piled up together. So the red line is f prime. I call it y prime, whatever. The black line is f of x, original absolute value of x. And that's that. And now in the homework, they get all fancy. with their questions. I give you a whole bunch of graphs to try to confuse you, but then you guys are good, so you know how to solve these things. Now again, this particular version of the book is the older edition. So if you are using the new edition of the book, you're not going to have the same numbers as what I have here. Oh, you can't see it. Maybe if I push the right button. To graph, this is the homework example. Sketch the derivative. This is exam 2 question, right? Sketch the derivative given the function. Black line is the function. So all we need to do is to draw the derivative. Now, obviously, out of all colors, the only one that I'm missing is red. So I guess we'll go blue. Nice. So, vertical asymptotes are preserved in their spot. So the derivative will have the asymptote at the same place where those asymptotes were before. So that doesn't change. What do I have next? The next is to draw all minimum and maximum values. We draw zeros as x-intercepts, right? So let's say there is a maximum right here. So that will give us the x-intercept at the origin, right? Great. And now we're going to use the rule of increase-decrease constant. The function is decreasing. Well, actually, the middle is easiest to solve first, because for the middle you have the point that the derivative has to go through. So this part is increasing. Function must be positive. And this one is decreasing, so the derivative must be negative, and we can make them follow the asymptote, right? It will eventually follow the asymptote. So now we have the middle solved. So one side is going to curve up because the function was increasing, so the derivative needs to be positive. And then when you go through the point, function becomes decreasing, so it has to become negative. Now, the next one over here, we have increasing function. We have a decreasing function, which means derivative needs to be negative. It's a decrease over here, and over here is the decrease as well, so another negative for the derivative. We do not cross x-axis with those end pieces because end pieces do not have min and max for us to have the point on the x-axis to go through like we had in the middle. So the middle has a maximum, and because it has a maximum, it has a point through which the graph is going to pass through the x-axis. And the other ones, the end ones, are as what they are. So that's the homework example. Whole bunch of these homework examples, you guys to practice. This is raised, what you see there, that's the raised absolute value of sine, right? Raised up. So that will be a sine plus 2. Absolute value of sine plus 2. And then you have this one, right? You have this one. There's another rule that we don't stress on now. We could, and that is the one that anytime you have the sharp corner like this, there is no derivative there. Because at that point you have two competing slopes. You see the slope incoming from the left is -1, slope on the other side is +1, and you can't have -1 and +1 at the same spot. So there's a competition between those two. So anytime you have a spike like that, there is no derivative. Use the open circle. If you look at my absolute value of x, I have open circles on both. I have open circles on both of these. Usually you fill one in, right? The black dot. But the function is not differentiable at 0 for absolute value of x because, as I said, from the left, it wants to be -1. On the right, it wants to be +1, and we know there is no limit, right? The derivatives are calculated through the limit. So the homework will open at some point after the exam. I just need to show one more time what to practice because I won't see you till Monday, and then it's way too late. So let me just shut this off. Say bye to tens of millions of people. They should smash the like button, right, and so the sub notification bell. Come on, shut it off.